Now we proceed to a fairly simple equation. And let's put a date on here. We proceed to a fairly simple equation, y double prime minus 2y equals cosine t. And we solve the homogeneous equation. Okay, we're going to apply the method, the variation parameters method, to this equation. Now this equation, I will note, is easily solved using undetermined coefficients. You just simply assume that y, in order to get a cosine t, y double prime could be a cosine, and y could be a cosine, some multiple of a cosine, and you find out pretty quickly that the solution to this is negative 1/3 cosine t, using a very simple method. So we have a way of checking ourselves, and everything didn't work out here. Maybe in going through this I'll be able to identify what went haywire when I worked this out, which I did fairly quickly. Okay, so we solve the homogeneous equation and we get r equal plus or minus 2, our fundamental set, e to the square root of t, 2t, e to the square root of 2 times t, e to the negative square root of 2 times t. Okay, now, that means that our y1, y2, y1 prime, y2 prime matrix is this. Don't have to read that to you. The determinant of this, you can easily verify, is negative 2 square root of 2. I don't have to tell you why that is. The inverse then is, well, flip these two and change the sign of each one. Well, it comes out here. I wrote out kind of the formula for that. But if we flip these two and change the sign, and that's where I didn't, no, I'm sorry, we flip these two, we don't change the sign. And we change the sign on these two, and we have the inverse matrix as long as we divide by the magnitude of the matrix, the determinant of the matrix. Okay? And again, I did a calculation, and I wrote this down when I figured out this times this gives us negative square root of 2 over 2, which divided by this gives us 1, and so forth. Just verifying that this times this gives us the identity. So I'll just kind of cross that out now, not that it's invalid. It's not part of our solution, but we do want to verify that we've correctly inverted the matrix before we go to all the trouble of doing the rest of this, and most of the trouble is in the integration. Okay, we don't want to do all that integration and then find out that we messed up our determinant. We left off a negative sign or something, the way I often do. Okay, from this then we get u1 prime, u2 prime is our inverse matrix times our 0g of t matrix, g of t being our cosine of t. And we multiply that out and we get this, which I do believe is correct. Now, that tells us that u1 prime is the square root of 2 over 4 e to the negative square root of 2t times cosine t. That's our u1 prime. Our u2 prime is this. I don't have to read it to you. So that u1 is the integral of this, and u2 is the integral of this. Now, how do we do that integration? And I didn't actually do the integration in class. I let the class work on another problem while I tried to quickly go through the integration here. I think I messed something up. I'll go through the details of it. First thing I did is I didn't actually integrate this. I integrated e to the kt times cosine t. Okay, and that's a straightforward integration by parts. Why do I do that? Well, because I have an e to the kt cosine t here and an e to the kt cosine t here. So both of these integrals are going to be instances of the integral of e to the kt cosine t. So why should I do two different integrals when I can do one and then just use the appropriate values of k to get the result? So follow me, because something's wrong here. Something didn't quite work out here. It almost worked out, but the negative signs are in the wrong thing, and I still don't know why. Okay. Letting u equal e to the kt, du is k e to the kt dt. Lock that in, that's got to be so. dv is cosine t dt, that dt is hard to read, cosine t dt. So and this is all kind of run together here, but that means that v is sine t. So what do I have? I have uv, which is e to the kt sine t, minus the integral of v du. Well, that's going to be a sine t e to the kt, and there's a k that I can put out in front. And that's what I have here. And if there's a mistake with that, I don't see it. If there's a mistake earlier than that, maybe that's the explanation why this didn't work out the way it should. But it all seems pretty straightforward. Okay, well, u equals e to the kt, du equal k e to the kt, and dv sine t, and v is then negative cosine t. So we have, what, e to the kt sine t minus k times this integral, so minus k, and then all the rest of this is going to be the two parts of this integral. We have our v du, which is negative cosine t e to the kt. And it appears that I left a k off of this, didn't I? So my v du, well, okay, never mind. No. My uv is negative cosine t e to the kt. I don't know why I was looking at that. It's still under the effect of whatever's messing me up in class. Okay, that's our uv. That's correct. And then our minus integral of v du, there's the k e to the kt times negative cosine t. Now we've got to be careful about signs, and this is where I suspect that I made a mistake, but I'm still not seeing it. So we have e to the kt sine t minus k times negative e to the kt cosine t. We can factor out the e to the kt, and we end up with sine t plus k cosine t. So I still believe what I have here. And I need to close this parenthesis. Okay, then I'm going to have a negative k times a negative k e to the k, and so forth, times this integral. Okay, I'm going to have a negative k times the negative of this integral. So I'm going to have this integral. But this integral has a negative in it, so I'm going to have a negative here. And it's going to be a k squared. And then it's the integral of e to the kt cosine t dt. I kind of had to string that down along here. I was not intending, when I did this, to actually point it out to people. I just kind of did it to show people how it works out, and it almost did. Okay, so now I've got integral e to the kt cosine t dt equals this stuff minus k squared times the integral of e to the kt cosine t dt. This integral is the same as this integral, except it has a negative k squared, and it's on this side of an equal sign. So I add it to both sides, and I get 1 plus k squared times that integral. And that's equal to e to the kt times sine t plus k cosine t. Well, that means that the integral of e to the kt cosine t dt, which would be this, is yeah, I thought I almost saw what went wrong, and maybe I did, but divide both sides by the 1 plus k squared, and you have this, so it's just the sine t, e to the kt sine t plus k cosine t over the quantity 1 plus k squared, and there's our integral. Okay, so for u1, that goes with the first of our. No, I may be starting to see something that I did wrong, because I was letting u1 be the one with the e to the negative square root of 2t. But yeah, there it lies. Okay, I'm going to stop here. I'll fix this and do a quick addendum. But I kind of mixed these two things up. And that's why this didn't work out. What I got was this and this. and I had a sine t minus the square root of 2 cosine t over 3 and all that. And remember that what we're supposed to get here is that our particular solution will be 1/3 cosine t. Okay, but it looks like if I'm adding the u1 y1 to the u2 y2, the exponentials cancel out, as I think they do. They just about have to get what we need to get. But the cosines were canceling out, leaving me sines, and that was not going to be good. So I want to fix that and come back.